All right, today we're going to crack open the coder's playbook. We're going to see exactly how programmers take these abstract ideas we all have and turn them into the actual powerful software that, let's be honest, runs our world. It's a journey of logic, creativity, and a whole lot of problem solving. So let's just dive right in.
I mean, it all really starts with a question just like this one. How does a simple thought, that what if there was an app for this moment, actually transform into a tool that you use every single day? That's the core mystery we're going to unpack together, step by step, from the very first blueprint to the final build.
To really get what programmers are working with today, you gotta look back at how their tools were made. And trust me, this isn't just some boring history lesson. It's the story of this constant battle against complexity as we figured out how to give smarter and smarter instructions to machines.
And that evolution basically happened in 4 big jumps. We started with first-gen machine language, literally just ones and zeros, the only thing computers actually understand. Then we got assembly, which was a little better, using simple codes like add or move. The real breakthrough was the 3rd generation with high-level languages like C, stuff that humans could actually read. And finally, the 4th generation gave us object-oriented languages, which were specifically designed to handle the massive, sprawling apps we use today.
And this visual just spells it out, doesn't it? On the left, you've got machine language. It's lightning fast for a computer, but for a human, it's a total nightmare to read or fix. And on the right, you have modern code. It uses words and logic and a structure that we can actually understand. This wasn't just about making things easier, it was absolutely essential to build anything more complicated than a pocket calculator.
But here's the thing, the language you use, that's only part of the story. As programs got bigger and bigger, the real challenge became organization. I mean, how do you structure a million lines of code so it doesn't just collapse into a huge mess? Well, this led to 2 major ways of thinking.
First up is what's called procedural programming. The best way to picture this is like a company's org chart. You've got the main program at the top, that's the CEO, and the CEO's job is to delegate tasks to smaller, more specialized functions down below. It's a very linear, very top-down way of looking at a problem.
So the name of the game here is divide and conquer. You take a big problem and you chop it up into a sequence of steps or procedures. The focus is all on the actions, the verbs of your program. The data, well, that's often just sitting out in a big shared pool that any function can dip into, which, as you can imagine, can get messy in big projects.
Now, the second philosophy pretty much flips that whole idea on its head. This is Object-Oriented Programming, or OOP. Instead of a top-down chart, I want you to picture a team of independent experts. Each one of these objects, like Object A, B, and C here, is its own self-contained little unit. It has its own data and its own special functions, and they solve problems by working together, sending messages back and forth.
The core idea of OOP, and this is the real game changer, is that you're building with digital Lego blocks. Each object bundles its own data and the functions that can mess with that data together in one tidy package. This makes your code way more modular, way more reusable. It's a bottom-up approach. You build your powerful, independent little blocks first, and then you snap them together to build something bigger.
Okay, so let's put these two side by side. This table really clears things up. You can see the total contrast, right? Top-down versus bottom-up. Focus on actions versus focus on objects. But look closely at data security. OOP is way more secure because it hides the data inside those objects. It's a concept called encapsulation. It's like a tiny vault. Only specific functions are allowed to get the key. This single idea made building the huge, reliable apps we use today actually possible.
Okay, so we've covered the history and we've covered the big philosophies. But how does a programmer actually build something? Let's walk through the practical, 4-stage game plan that brings a program from an idea into reality.
This is pretty much the roadmap every developer follows. You start with design, that's the blueprint. Then you have coding, the actual construction work. After that comes the really critical phase, testing and debugging, where you hunt down all the things you did wrong. And finally, you analyze for efficiency, to make sure your program isn't just right, but also fast.
Let's zoom in on that testing phase for a second, because let's be real, no program is perfect the first time. It's going to have bugs. And programmers are basically professional bug hunters. They're usually on the lookout for 3 main types of these little critters. The first, and honestly the most common one, is a syntax error. This is basically just a typo or a grammar mistake in the code. It's like forgetting a period at the end of a sentence. The computer just gets confused, it has no idea what you mean, and the program just refuses to even start. It's annoying, for sure, but they're usually pretty easy to fix.
Okay, so the next level up is a runtime error.
Now, your code's grammar is perfect, but while the program is actually running, you ask the computer to do something that's just impossible. The classic example is trying to divide a number by 0. The program starts up just fine, and then, bam, it crashes the moment it hits that one impossible command. These are a bit more serious because they can happen right in front of a user.
And then there's the sneakiest, most devious one of all, the logical error. With this bug, the program runs perfectly. No crashes, no error messages, but it gives you the wrong answer. Maybe it told it to add when you meant to subtract. The computer did exactly what you told it to do, but what you told it to do was just plain wrong. These are by far the toughest bugs to find.
So you did it. You built your program, you squashed the bugs, it works, you're done, right? Well, not quite. In the real world, there's another boss you have to answer to, and that boss is time. See, being correct isn't enough, you also have to be fast. And that brings us to that final, all-important stage, efficiency.
And this graph, man, this graph shows you the brutal cost of a slow solution. Those green lines down at the bottom, that's efficient code. As you give them more and more data, their runtime grows slowly, nice and predictably. But look at those red lines. Their runtime just explodes, shooting almost straight up. An algorithm that feels instant for 10 items might literally take centuries to finish for 1,000,000.
This table kind of puts numbers to that explosion. Programmers use what's called Big O notation to describe how an algorithm's speed changes as you throw more data at it. An O log n algorithm is excellent. Its time cost barely even budges. But as you go down that list, the growth rate gets terrifying. And catastrophic is not an exaggeration. It's the difference between your app finishing in a second or after the sun burns out.
And in the real world, this isn't just theory. There's a hard penalty for being slow, and it's called time limit exceeded, or TLE for short. Your logic could be perfect, your code might produce the right answer eventually, but if it takes too long, it fails. For a website, a stock trading app, or a video game, being too slow is basically the same as being wrong. So this is the modern programmer's dilemma, right? How do you manage massive complexity, but also satisfy this ruthless demand for speed? Well, to win on both of those fronts, you need a special kind of tool. And that, my friends, brings us to C++.
The philosophy of C++ is really the end of the journey we've been on. It completely embraces object-oriented programming to handle complexity, dividing programs into objects, protecting data. But its absolute killer feature is that it combines that high-level organization with direct, low-level control over the computer's hardware, giving developers the best possible performance.
And we are not just talking theory here. Look at where this power gets used in the real world. It's the backbone of your operating system. It's the engine behind blockbuster games made with Unreal. It's the brain in high-speed financial trading systems. It's even the critical code that's keeping airplanes safely in the sky. When performance isn't just a nice feature, but an absolute non-negotiable requirement, this is what developers turn to.
So, we've gone all the way from a simple idea through different philosophies and workflows to a tool that's built for the toughest jobs on the planet. C++ really shows us that the coder's playbook is all about picking the right strategy for the right problem. It gives you incredible power, but that power demands discipline. So I'll leave you with this to think about. What big, complex, mission-critical problem would you want to solve with a tool this powerful? Thanks for joining me on this one.